Hey Hadi, what are you doing, man?
Hey, come, join me.
What are you doing, Hadi? It seems like you playing something.
Yeah, I'm playing a very interesting game, man. It's very fun. Look, I'm trying to score this wooden block to that goal over there.
Oh Hadi, I want to ask you something. Why you play this game?
First of all, I'm very bored, man. Secondly, this game is actually related to our dynamic class. Do you know that?
Hi everyone, so today I'll be explaining on how the rubber band and wooden block game is related to our dynamic class. So firstly, this game involves the movement of object, which is the wooden block. So the movement of object is caused by the transformation of energy, which related to the law of conservation energy. What is law of conservation energy? Law of conservation energy states that energy cannot be created or destroyed but can be transformed in one form to another form. For example, in this case, the wooden block is moving from the releasing point to the goal point. This is caused by the transformation of energy from the elastic potential energy in the rubber band that is transferred to the wooden block that cause the wooden block has the kinetic energy to move in acceleration. Next, the energy that is formed and lost can be calculated by making assumption for the value of all parameters needed. For example, in the formula of the kinetic energy, we need the mass and velocity, and the formula of elastic potential energy, we need the spring constant and the stretch of the spring. Next, we can know that in the system, the energy does not conserve. As we make the calculation, the energy transform from the elastic potential energy to the kinetic energy is not equal. So this means that there is loss of energy. We conclude that the loss of energy is formed by the friction force from the surface to the wooden block.
Oh, like that.
Yeah,
So can you share with me how this thing actually work?
of course, man. Yeah, it's really simple, man. When I move this block backward, this rubber band will store potential energy.
Oh,
Thus, when I release it, it will then convert the potential energy to kinetic energy.
oh, in that case, so I guess there's many application using this thing.
Yeah.
So can you share some of them?
Of course, there are actually many applications of this. For example,
Next, the application or other related example is slingshot right, and the crossbow. The application is the same, whereby the elastic potential energy from the rubber band is transferred to the object so that the object have the kinetic energy to move. So I think that's all. Thank you.
So Hadi, I have one last question for you. So can you tell me in detail how this thing works actually with all our knowledge about dynamic that we have learned?
sure, it's actually like this.
Hi, I am HAKIM, and I will discuss about the free body diagram and kinetic diagram. I will cover both of them. Okay. First thing first, we go to the free body diagram. Okay, from our introduction, we can see what we are trying to calculate, to discuss. Okay, we want to discuss about the slingshot. Okay, this is free body diagram where we have a rubber here, and then we have the wooden block here. Okay, wooden block had a dimension of 0.1 meter and 0.02 meter width. Okay, before that, we will talk about the mass of this block is 0.3 kg or 300 gram, and the K of the rubber band is the 90.8 Newton meter -1. So first, you will see there is the line which we call it a datum. Datum is our reference point, which is the starting point for our mechanism. And then when we try to pull the rubber band with the block, the distance is 0.08 meter. Okay, we are done with the free body diagram, and then we will continue with the kinetic diagram. Okay, from this diagram, we can see that the data what we're talking about is this. Because when we release our potential energy, the rubber band will go back to its initial form and go back to its datum. Yeah. In our kinetic diagram, we can see that the block moving to the front, and it has its MA, which is F equal to MA, and the distance the block is traveled is 0.1 from its datum. Okay. We also get the velocity of the block, the moving it forward is 1.5 ms/1, which is the unit for velocity. Okay, that's all from me, and I'm out.
Okay, so hi, today I will be covering the calculation part of our case study. So here I've listed all of the symbols and what they represent, and this is the formula for elastic potential energy, and this will be the formula for kinetic energy. So as you can see, this is formula of conservation energy, and this is what we are being studying today. So in this case, we already known all of the unknowns for m, v, small k, and x, meaning that in our calculation, we are just to compare the principle of conservation of energy in theory and real life. So when we input all of the value, k equal to 90.8 and x equal to 90.8 Newton per meter, and stretch 0.09 meter. When we input in formula, we get this value. So this is the potential energy of U1. Actually, it's for U1. So, and then we calculate the kinetic energy, and this is for K2. So we input the mass equal to 0.3 kilogram and the velocity equal to 1.5 meter per second. So as you can see that our parameter already in standard and SI unit, so no need for any conversion. So for K1 and U2, both of them will be equal to 0. Okay, why is that? It's because in the system, you can refer it to the free body diagram. The object initially didn't move, so we just stretch it. We just stretch the rubber band along with the object to store potential lasting energy, meaning that the velocity will be 0. And if you take a look at the formula, the initial kinetic energy, or K1, will be equal to 0. As for U2, the object is when we already release the rubber band. So, or therefore, the stretch will be 0, meaning there is no potential elastic energy. So at the bottom, as you can see, the value, it's supposed to be same. Both of them supposed to be the same, but in real life, of course, in theory, of course, it should be the same. It should be ideal, but in real life, this thing is inevitable, meaning that there will be some energy loss, or energy is converted into other form of energy, for example, heat energy, sound, and so on. So at the bottom part here, I already calculated the efficiency, or actually down here is the energy loss, energy that is not converted into supposedly kinetic energy. This when we input the value is 8.213%, or we can say that the efficiency of the system is about, the efficiency of energy is about 91.7%. Okay, that's all for the calculation part. Thank you.